Okay, today I'm going to give you guys a little bit of a tutorial on how to think about kinetic and potential energy and the law of conservation of energy. First off, we have to understand the law of conservation of energy. And the law of conservation of energy states that energy cannot be created or destroyed. And we have to really clue in on the word destroyed because energy can be lost as far as its usefulness, but ultimately it is not destroyed. It is just distributed somewhere else. In a lot of cases, loss of useful energy comes from friction. Right now, I'm going to show you a demonstration where we ignore friction for a little bit and kind of show you how things convert from potential energy to kinetic energy as they move throughout, in this case, a skate park. I take the skater and place her on the skate park ramp and notice the graph of energy over there. Right now, the total energy is all potential energy. So what happens if I let go of this skater? Notice that the potential energy gets changed into kinetic energy as she moves up and down. Conversely, the kinetic energy moves back to potential energy as well. So let's watch this for a second, and I want you to think about when is the kinetic energy growing and when is the potential energy growing? Conversely, when is the potential energy decreasing and the kinetic energy decreasing? Well, as we can see, if we watch this closely, as the potential energy is decreasing, the kinetic energy is increasing. So they are converting from potential energy to kinetic energy. And when the kinetic energy is decreasing and the potential energy is increasing, the conversion is just the same. Now, where is the potential energy the highest? When the skateboarder gets to its highest point on the ramp. Conversely, the kinetic energy is at a maximum at the bottom because the speed, I'm going to put the speed up here now, and we can see as it moves up, the speed decreases, while as the skater moves downward, the speed increases. Well, we know that kinetic energy is, or the kinetic energy equation is 1/2 mv squared. So the velocity is directly proportional, well, more than directly proportional, but it is proportional to how fast the skater is skating. So the kinetic energy goes up as the speed goes up. And then as the skater goes up the ramp, they slow down and the kinetic energy decreases. Well, as it goes up, the potential energy increases because potential energy is mass times gravity times height. So as the skater gets higher and higher up the ramp, the energy becomes more and more potential. So hopefully we can kind of see that by this demonstration. Now, as I said before, that is without friction. Well, what happens if we add some friction to the skater? What happens over time? What do we see happening here? The potential and kinetic energy are decreasing over time, and the thermal energy on the graph is increasing to the point that it finally becomes the total energy of the system. Well, why is that? Well, as I said before, friction causes a loss of useful energy. And friction does that by converting mechanical energy that is being caused from even they're scraping, even with the wheels rolling pretty freely, that over time the energy gets transformed into heat, which is no longer usable by the skater. Again, watch this one more time as I move the skater up. We have friction going, and each time the skater switches sides, she goes up a little less every time until she finally bottoms out at the bottom because all of the energy is lost. So hopefully this kind of can help you think about what's happening when you get to your conservation of energy assignment and you start having to think about a child in a swing or a child on a slipper slide. The concepts are all the same. Think about where the potential energy is the highest. Where's the kinetic energy going to be the highest? Where's the kinetic energy going to be the lowest? Where's the potential energy going to be the lowest? These are all things that you need to think about. So hopefully this will kind of help you understand a little bit. One more thing I want you to look at is if I stop right here, notice we have more kinetic energy than we do potential energy. If I had been able to stop that at the halfway point, what do we think these two bars would look like? Well, coming halfway down the ramp, by the time it's at the halfway point, the potential energy is now half of what it was because the height is half. So where did that other energy have to go? It had to go to the kinetic energy if we ignore the thermal. Maybe I ought to show you that real quick. Get rid of the friction again, and we'll let it go up and see if I can catch it halfway up. Well, not quite, but close. So as you can see, at the halfway point, the potential energy, half the height, would have half the potential energy that it had at its maximum height. Well, where did all that energy go? It went to kinetic energy. So that kinetic energy has half the energy, and the potential energy has half the energy at the halfway point. And that just changes as we move up and down throughout the curve. So hopefully this will help you with your conservation of energy assignment and kind of how to think about that slipper slide and the swing idea that you have to describe the energy change in that scenario. You have a wonderful day. Thank you.